Good day. I'm Mark Vickers, a technical director with Improving, and today I'm going to talk to you about resilient payments delivered in real time, proven quick-to-market solutions brought to you by Improving. On the agenda today is payments modernization, why it's a topic of interest now. We'll talk about the challenges and opportunities presented by any payment modernization effort. We'll speak about the proven solutions we've used in the past for payment modernization implementations. And we'll talk about the bright future that is available to us when we use the right architectural approaches when we develop a payment solution. Modernization, real-time rails and connect. So if you're in the Canadian banking scene, you're no doubt aware of two recent initiatives. Real-time rails, a government-mandated initiative to enforce sub-second response times when processing online banking payments, where we're targeting something on the range of 750 milliseconds. Another initiative is Connect. This is a collaboration between Canadian banks and Interac with the purpose of extending banking service to remote and northern communities, and with another goal for allowing Canadian banks to take on PayPal. So if you think of when you make an online payment and you see PayPal as an option, the goal here is to have a separate option for allowing Canadian banking clients to do direct payments through their bank, with an idea here of making payments as easy as tap. These two initiatives together raise the bar for any new payment solution that a bank develops. So not only do they have to have extremely low processing times, they also need to be as reliable, scalable, and efficient as PayPal is today. So this raises the bar for any new Canadian payment implementation. So what are the challenges when we develop a new payment solution? So payment systems need to support synchronous calls that wait for a response. And these calls often involve multiple steps, many of which cannot be performed in parallel. So the challenge here is to make efficient use of compute resources when you are servicing these synchronous calls. Another challenge is to have concurrency controls in order to make payments cancelable. So the idea is to be able to safely unwind or stop a transaction that has previously been started. A further challenge is in the area of scale. So it's one thing to develop a payment solution that can handle 1 or 2 transactions per second. These sort of solutions sometimes fail when you ratchet up the scaling to 80, 100, or 200 transactions per second. More is simply different, and they require a different architectural approach. So in addition to servicing synchronous calls efficiently, supporting concurrency controls for the purpose of cancellation and being scalable, new payment solutions also have to handle failure resolution. So the idea here is that when a call fails, you need to retry until it's successful or unwind it in the event of failure. And there's a certain tension being able to support synchronous calls at low latency while also allowing for retriability. There's one thing we can count on when we develop in distributed systems. It's that failure is inevitable. You can't hide from it. You can't prevent it. Remote calls will fail, processes will fail, machines will fail, systems will fail. And given that failure is inevitable, it can and will happen. The only thing we can do is embrace it, anticipate it, and design systems that account for it. When you're developing a new payment system, the following things need to be top in mind. You need to be able to answer yes to the following questions. Can your payment system pick up failed transactions, moving them forward to conclusion or unwind them safely, even in the event of a hard crash? Are you able to use chaos testing to a system under load where you have confidence that any in-flight payments that have been interrupted will recover? Are you able to upgrade your production system without affecting in-flight payments? Can you refine existing payment flows on your payment system without a complete rewrite? And can your payment system scale and scale effortlessly? This is a level of excellence that any new payment initiative needs to aspire to. Together, these form this set of requirements when you develop a new payment solution. It needs to support low latency response times. It needs to be able to scale both for today and for tomorrow. It needs to be responsive at all times, no matter what failures happen on the back end. And it needs to be resilient in the face of those failures, recovering transactions, unwinding them, or bringing them forward to conclusion. We need to be able to support zero downtime upgrades of your payment system, and we need to develop systems that are flexible to change. These together are table stakes for any new payment system that's developed. It's what's necessary in order to be competitive with your Canadian competitors and to compete with the likes of PayPal. Okay, meeting the challenge and making your opportunity. The good news is that We and Improving have helped banking clients deploy exactly these sorts of systems. The question is, what sort of principles are these payment systems built upon? And what architectural approaches can we leverage to support these principles? And when we use the right architectural approaches, what else becomes possible in the future? At Improving, we tend to use the following approaches when developing payment systems. They should be reactive. They often support event-driven architecture along with event sourcing, and they often employ actor systems. When you're developing a reactive system, the idea is to have a system that is responsive at all times. So this means that no matter what challenges you face in terms of scaling up demand or scaling back down, and no matter what sort of resiliency challenges you face, whatever crashes, you need to be responsive to the client channel, meaning that you need to be able to respond within a low latency period of time, even if that response is in the negative, saying that a problem has happened. So in order to meet that responsiveness goal, you need to have a system that is both elastic and resilient. So being elastic means that you're able to scale up your system or scale it back down to meet demand as it fluctuates throughout the day. You also need to develop a system that is resilient. And this means giving the possibility of failure, treating it as a first-class concern, and being aware of all the possible modes of failure that might happen in your system and accounting for it. And underlying all this, you tend to have a message-driven system. And this is a technical consideration that we'll speak on more later. When you're developing a system that's responsive, particularly if you're on the JVM over the last 20 years, so when you're trying to produce a payment system that has the ability to seriously scale, this meant you've typically reached for some sort of reactive framework on the back end. The idea is on the JVM, if you block on a platform thread, which is a scarce resource, this should be considered a fireable offense. And this is because the only way to be able to scale is to make efficient use of these platform resources. So traditionally, when you're on the JVM, this means reaching for something like an actor-based system, such as akka, which is asynchronous in nature. Or if you're in the Spring ecosystem, you're using Reactor or something like Webflux. Now, the good news today is that it's never been easier to build a responsive system. So while using an actor-based system such as akka or using the Spring ecosystem with Webflux, these are still great options today. You also have the option of using virtual threads now. And virtual threads give you the ability to code in an imperative style, which many devs find more approachable. Now, when you're using virtual threads, you still need to be able to account for the error channel, and it doesn't address all of your concurrency concerns. But it's nice to know that you have some other options beyond actor systems or Spring, if that's your choice. Another principle for building a reactive system is having the ability to be elastic. So this means being able to scale up and down to meet demand. And this, again, is table stakes when you're developing any new payment system. It's easy to accomplish elasticity, whether you're on cloud or on-prem. You've got options such as using Kubernetes for pods, where you're triggering based on request rates or CPU processing time. Or you can use a serverless option. In each case, you're minding your cold start. So if you're using Kubernetes and pods, you're making sure that your pod is ready before you direct traffic to it. If you're using a serverless system, maybe you're leveraging something like JavaScript or TypeScript to minimize your cold starts as an option. Either way, you're going to be favoring systems with sharding support or with partitioning support for easy horizontal scalability. So this means using something like um, Kafka for messaging, which supports partitioning across different pods. I'm going to pause here for a sec. I've got a bit of a cough. Okay. Okay, the next principle when you're developing a reactive system is resilience, and this means modeling failure as a first-class concern. So at a practical level, when you're looking at remote calls in your system, you're looking at them as potential sources of failure. Anytime you're dealing with any sort of IO, it could fail, and you need to account for it. So when you're looking at the very low level method level, you want method signatures that present failure as a possibility. You don't want to hide that away. And as a distributed systems engineer, it pays to adopt a pessimistic mindset at all times. This means you're considering all the ways in which your system might fail. You're considering component failure, process failure, pod failure, on and on. You're also planning for the isolation of failure, and you're reaching for tools such as circuit breakers, which allow you to detect and reject some traffic in the event of a failure. Or you're working with frameworks that support back pressure. So the idea here is if a downstream component fails, you need to be able to recognize that upstream and ease off on the traffic that you direct so you don't overwhelm the downstream system. Often when we're developing for resilience, we're reaching for something like event sourcing or event-driven architectures. This gives us the ability to have persistent entities which record a series of events and accumulate them over time. And in the event of failure, you can replay those events in order to bring an entity back up to present. And this couples well with projections, which give you the ability to rehydrate those entities in the case of failure. This allows you to have durable payment workflows. I'm going to pause again here for a second. If you're not using event sourcing, you're still going to want to consider the use of something to allow for your payment workflows to be durable. So some options in this area are, for example, temporal, or if you're working with a cloud-based system, each cloud provider tends to have some sort of durable workflow offering, such as AWS step functions on Amazon. So either way, you need a mechanism to restart payments in the event of failure so that you can either unwind them or drive them forward to conclusion. No matter what resilience options you choose, you should be elevating failure handling beyond just the dev team. The notion of failure as a possibility should permeate the entire software development lifecycle. All stakeholders should be involved in the failure concern. So this means business analysts should be aware of it, and the stories that get crafted should both anticipate and reflect failure. Any unit test written by devs should account for the unhappy path and should codify the handling of failure. QA must be empowered to test for failure. And ideally, chaos testing should be used both by either by QA or by SREs so that you can validate the handling of failure no matter where in the process a failure might happen. The final principle when you're developing a reactive system is to be message driven. And this is the foundation upon which we build systems which are easy to reason about. And what makes it easy to reason about is that events are immutable, so that they should not be able to change over time. So that makes dealing with process flows simpler. There's many different options you have when you're employing message-driven systems. So for example, Kafka, ActiveMQ, SQS on the Amazon world, PubSub on the Google side. So in addition to being reactive, we like to use actor models when we implement our systems at improving. And this checks a number of the reactive principles. So when you're using actors, you have the ability to be resilient because each actor, if it fails, has a supervisor which is able to restart that actor in the event of failure. In order to be elastic, there's the notion of location independence. So persistent actors can be relocated as needed. So if you have a pod or machine failure, any actors that were resident on that pod can be moved to uh, another existing pod, or a new pod can be started up and actors can be rebalanced. So that provides you the ability to be both resilient and to spread load across new machines in the event that you need to scale up, or they can be relocated if you are intending to scale back down. Actors also support the ability to be responsive with their asynchronous programming model. And on top of everything else, they're message driven. So each actor has a mailbox, which allows for the processing of one message at a time, which provides you concurrency control. So when you're considering cancellation in a payment workflow, this is the mechanism by which you can safely accomplish that. Event-driven architecture is another tool that we find ourselves reaching for when we're developing payment solutions. Event-driven architecture allows you to be loosely coupled between components when you're integrating them. So if you think of each component, it can generate a number of events, and these events can be broadcast as a stream. And downstream components can decide what, if anything, to do with these events. You can further use event adapters to enforce decoupling between these systems. So the idea here is that components don't necessarily need to talk to each other directly. That communication can be separated in time. Events are also immutable in event-driven architectures. These are things that accumulate, and this is helpful when you're doing the persistent back end. Instead of processing state in place and changing it as you go, you're instead accumulating a series of facts that are layer on top of each other. And this allows you to preserve intermediate state, which is handy both when you're debugging or when you're trying to paint a picture of a system at a later point in time. You can figure out at any point in time what your entities were up to. When you're doing when you're using event-driven architecture, also with event sourcing, often you'll have persistent entities, which you can use then to replace state and to catch up in the event of failure. When you're using event sourcing, you also have the benefit of potentially separating your reads from your writes. And this is known as CQRS. This is Command Query Responsibility Segregation. So when you're working on the right side of the equation, you've got the option to have a queue of commands. And this gives the possibility of retrying commands in the event of failure. When you process each command, you're going to write one or more events to a log. So you're accumulating events as facts, immutable events that build up in your persistent store. You can also use this event stream to project out to downstream components, which allows for that loose coupling that I was mentioning before. Your event stream can further be repurposed as a projection mechanism to feed into your read sign. So the benefit of this is you have a separation between your reads and writes. And this means that you can optimize your reads and your writes independently. So on the right side, you're often using, for example, a NoSQL event store, such as Cassandra, which allows for extremely high throughput on writes. Separate from that, your read projection can have dedicated table schemas for each use case on the read side. And this gives you the ability to optimize each use case independently on the read side. So when you use event sourcing in this way, you get the benefit of these event streams, and they not only help solve the current problem, but they allow you to future-proof for new requirements. And so you can future-proof with an event-driven architecture in CQRS. If you've ever been involved in developing an AI model, you know that AI is extremely hungry for data. And you have the ability to feed your AI with event streams when you're ready to. So the beauty of using event sourcing is that you benefit from the responsiveness, resilience, and scalability of that system to solve your payment needs today, but you also preserve the optionality for using those event streams in the future. And you can use them to train AI models, or you can use them in a more traditional machine learning sense to build up predictive analytics. So as mentioned before, when you use event sourcing, you have a stream of events which are immutable facts which you lay down. And this is different from traditional systems where you mutate state and place in your persistence layer. And this means that you can preserve intermediate states, as I mentioned before. So when you use event sourcing in your payment system, in your payment engine, and also in your integration components and throughout your software, your system, you're able to paint an accurate picture at a point in time, which helps you to answer various predictive analytics questions. So an example of this is a open source project called Quine, which is backed by a company called ThatDot. And it gives you the ability in the payment space to consider the possibility of fraud prevention. So Quine is a real-time messaging system that consumes messages and pushes them into a graph backend, which allows you to apply graphing intelligence to a system of events. Now, Quine also is reactive in that it supports being message-driven, elastic, resilient, and responsive in the same way as other tools that we have preference for in our payment solutions. And when you use Quine to answer the question of fraud, you're able to reduce the mean time to answers. So this means that you can answer the fraud question more quickly. And this turns the question of fraud on its head when you're developing a payment solution. So instead of approaching fraud post facto, where you're detecting fraud after the fact, with Quine, you're able to use real-time messages to turn it into the notion of doing fraud prevention, which is a great benefit. You're able to stop fraud before it happens. So in summary, payment systems should be both real-time and resilient, and that is very achievable today. Reactive principles lead the way in this regard, and the right architectural approach to providing these solutions can not only solve your current payment issues, but it can be leveraged in the future to support AI and machine learning and predictive analytics. If you have any questions about how improving can help you with payment systems or similar systems in the future, contact us at sales@improving.com. I'm Mark Vickers, a technical director with Improving, and thank you for your time today.